Alright, so streaming should be on now. Might take a while to see it. Yep. Okay. See, it's on. There we go. All right. And Luke is typing something. I'm not sure exactly what is power play 2x, 3x, and so on. You know, that's sounds like more gimmicks to me. All right, we got about a little less than 2 minutes to go. All right, so let me close that. 9 ways to win. All right, so all prices. It's I just find this pretty amazing of how the lotto um, organization is trying to convince people that $40 million is a lot of money. I mean, I don't doubt it. I mean, $40 million is a lot of money. The question is, are you, on the average, are you losing money, buying lotto tickets? So that's the funny part. Odds of winning is 1 in 25-ish. All right. Anyway, we got about 20 seconds to go. Right, exactly. I mean, if they want to teach you probability, they probably could have said something about the the chances of getting killed by bee sting. As it turns out, more people die from bee stings each year than there are people dying from shark bites. Yep, that's a pretty unlikely kind of thing to happen, but the likelihood of winning a jackpot is even less. So there is that. The chances of getting into a fatal car accident on the way to purchase a lotto ticket may be higher than winning the jackpot, of a lotto ticket. So, um, I'm pretty sure they don't want to publish those numbers. All right, so it's time to get started. I am going to go through this. I mean, I don't really have a whole lot of planned items. Just kind of continuing to move on to terms of counting, and then go to the equations, and then go to the expressions, and so on. The first question is: are there any questions about the C and F assignment? Now, I do get a few questions. I think the most common question about CNF is, how do I get more opportunities to practice? Okay. The thing is, you can actually come up with your own random Boolean expression. Just kind of throw in six, five, six variables, and then just come up with your own. I mean, it's like, oh, I think I can put a little conjunction here, and then that term of conjunction is going to be the left hand side of the implication, and then on the other side of the implication we have a negation of blah 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 blah. I mean, you can easily come up with a random Boolean expression. So the question now is, given a random Boolean expression, and you're going through the process, right, to convert it into conjunctive normal form. So the question is, how do you know you're not missing something along the steps, right? How do you know the expression that you start off with has the same meaning as all the um, intermediate expressions, and all the way down to the C and F. So there's that question. Um, So I'm gonna let you guys think about it a little bit. I have an answer to that, but I want you guys to think about it and see if you guys can come up with a way so that you can actually verify that every single step along the way you are coming up with expressions that are equivalent to the original expression. So we got a few people typing, which is good. So I'm going to wait a little bit here. And while I'm doing that, let me go ahead and get started with a tool, a magical tool that can help in this case. Now you guys can do it in many other ways, but this is one way to do it. You obviously can do it in many other ways. So I'm going to start up Calc here, which is a spreadsheet program. All right, so we got Elijah saying truth table. Yes, so truth table is the correct answer. Maybe not for every line, but to compare the end with the start. You can compare every line, it's just that you have to basically enter the intermediate expression as an expression so you can check against it. So that's one way, absolutely. So Elijah is correct. And then Philip said there are quite a few YouTube videos online that give good examples and walkthroughs of how to prove both CNF and DNF. All right, excellent. So I'm going to give you guys an example, just in case anyone wants to know a very specific way to do it. So I'm going to give you a very specific example here. It's not going to be too complex because I really don't want to spend too much time to do this. So we're going to have P. Okay, I'm going to use the easy notation, because that's just a whole lot easier to deal with compared to LaTeX notation. So I'm going to have a P implies Q. Let's see here, or P Q and not R. And I'm just randomly making something up here, obviously. So this entire thing implies, let me see. I want to do something that's a little bit harder. So we'll have R, not S, and T over here. There we go. Okay. So this is the problem that I'm giving myself. And once again, I'm using the shorthand, right? So what looks like addition is actually disjunction. What looks like multiplication is actually conjunction. And they're following the same rules as, so multiplication usually happens first. And in this case, your conjunction also has a higher priority compared to disjunction. Oh, okay. So Rayshawn is asking Philip, are there any you'd recommend? Okay, so I will leave it up to Philip to answer the question if he wants to. All right, so this is the starting point, right? So the question is, how do I enter this into what is it? How do I enter this into a way, a mechanism, a tool? Okay, so implication is a little bit hard because most languages do not have implication as an operator. So that's the one that you probably have to convert into a negation followed by a disjunction. So we're going to convert that one first. And there are two in this case, so we'll go ahead and do one at a time. So we have not P or Q, which is P implies Q. And I'm going to leave the other ones alone, right? And then this entire thing is the left-hand side of an implication. So that means I'm going to negate this entire thing, and then or the right-hand side of the implication, which is R not as T. It's basically R and not as and T. So there we go. All right, so now that we have an expression that is usually doable in most programming languages, so what you can do is you can write a program, right? You can just write a C, C++, Java, JavaScript, Python, Perl, just take your pick, okay? So you can do it with a program, and what you need to do is to iterate through um, all 32 ways of assigning values to PQRST. There are only 32 because there are 5 independent Boolean variables, and 2 to the power of 5 is 32. Okay, so that's one way to do it. So every step along the way, you can modify that program, right? And just say, okay, this is the next expression, and I want to make sure that this expression is going to be um, equivalent to the original one. So you basically just every step along the way, you're adding more and more expressions to check by evaluating these independent variables. So I would suggest using an array of Boolean variables, because that way it's easier to kind of iterate through them and assign each one to a different value. And then we got some questions in the text channel. Can you compare two expressions via truth table even if one expression doesn't have some variables that the other one has? The answer is yes, absolutely, because it basically, if a variable is not mentioned, then it has no influence to the value of the expression. So you can always throw in more variables into the whole mix. It's just that you end up with a bunch of rows that have identical values, because so if you just look at this here and you kind of imagine that we have, let's say, 2 more variables, okay, u and v. So you can see u and v is not mentioned anywhere here, right? So whether u is true or not doesn't really matter, right? Whether v is true or not also does not matter. So you just end up with a lot of rows that have identical values. Okay, so it's not a problem. Okay, you can always have the program to be able to handle more independent variables than there are actually independent variables in the expression. So that is not an issue. So basically, now, depending on what tool you want to use, if you want to use, okay, wrong place to do the editing. So if you want to do this, using a C, C++, or some programming language that is based on C, then you just basically translate this into an actual Boolean expression. So you have to use, not P, and then everywhere you see a plus, you basically replace it with a bar, which is OR, right? So you basically just do it like this. I mean, this is like, and then everywhere you have a quote-unquote multiplication, it is and, which is logical and, right? So it's not really super duper difficult. I mean, the translation does take a little bit of time, but it is not terrible. Okay, it's just that you just have to enter the expression into the C program, and every time you make a derivation, you enter that new expression, and then you just make sure that they are all for all 32 rows, okay, of the truth table, the two expressions end up with exactly the same value. So that's totally doable. Another way to do this, which is kind of the fun way to do it, is to use a spreadsheet. Yes, some of you already know that I'm quite fond of using spreadsheets to do things that people do not think spreadsheets can do. Especially those of you who are taking or have taken CISP440 from me, you know what I'm talking about. And for those of you who have not taken CISP440 and you're thinking about taking CISP440 from me, you can look forward to just kind of strange ways of using a spreadsheet. Alright, so there are many other ways to do this. One way to do this, this is actually one of my favorite ways to do it, is to have, okay, this is not the way I want to specify it. So I'm just going to end up with a bunch of cells that is essentially just incrementing, right? So we want to increment all the way up to 31. So from 0 to 31, there are 32 numbers. So now what we do, I like that. Well, I love not just spreadsheets, but Google Sheets, because Google Sheet actually supports regular expression to a very high level. And I'm not gonna waste time here to talk about regular expression, but I'll just say that it's a very powerful tool to process text, and it can do a certain degree of parsing. Yeah, I'm just gonna leave it at that. All right, so now we have P, Q, R, S, T, so each column represents one of the variables. So the way I want this is to have, P, the first 16 items of P to be, okay, it's easier to just have P to alternate between 0 and 1, and then Q to be, true, false, false, true, true, false, false, true, true, and then have R to be false, 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 true, 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 and then for S, it's like 8 false, 8 truths, 8 false, 8 truths, and then T finally is going to be like 16 false and then 16 truths. Okay, so you can go ahead and populate the table manually, okay, which is a killer. So instead of doing that, this is what I'm going to do. And if you have taken CISP440 from me, or if you have taken the class that talks about base conversion, I hope this reminds you of what it is. Okay, so we're going to take the floor of whatever this number is, okay, and I'll have to go back and fix the reference of the column number because that part has to be absolute, but we'll deal with that later. And then we'll have this one divided by 2 to the power of, and it's going to be the column number of the cell that I'm typing in right now, which is B2. So the column number is 1 oriented. In other words, column A is 1, column B is 2. So I need to subtract 2 from the column number because I need that to be 0 oriented. Okay, so now I close the power, and then I close the floor, and okay, I forgot about the mod because in the spreadsheet mod is a function instead of an operator, so it's kind of awkward, a little bit awkward, because when you say blah 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 mod2, instead of saying blah 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 mod2, you have to say mod and then the left hand side, comma, the right hand side. All right, so I do have one thing to fix, which is the reference of A, the column. So I put a $sign in front of the A because I need that not to change. So here comes a part of the magic is if I just kind of extend it like this, you should see alternating zeros and ones, which is the case, right? So here comes the second part of the magic, which is if I extend it this way, then we should see the pattern that I talked about earlier. So let's see if that. Oh, look at that! Ain't that cool? I think it's kind of cool. So now what we need to do is to code the expression that we were just talking about into another cell. So I'm gonna put it over here. So so if you have oh, you cannot because this is actually only on the local host. So I want to convert let's say this expression into a spreadsheet Boolean expression. So that is just a syntactical thing, because most spreadsheets do not support logical operators. So the logical operators become logical formulae, which are basically function calls. So it is just a hassle to do it, but it's not impossible to do it. So it's just a matter of you got to spend some time to do the conversion. Of course, some of you are smart enough to go like, so why do I want to manually do the conversion when I can write a tool to parse this kind of statement and then automatically convert it into whatever the spreadsheet needs to use? Sure, why not, right? So I'm just going to type the equation over here just so that you guys can see what it's going to look like. Okay, so in the spreadsheet, this is going to be, so you have to start with the equal sign to basically specify a cell is calculated instead of, what is it again? Instead of a literal constant, okay? So you start with the outermost operator, which is this OR over here. So now you say OR, and there are two things. So I'm going to automatically put in a comma, and then I go back and backfill what is on the left hand side of the OR and then what is on the right hand side of the OR. So what is on the left hand side of the OR is starting with a not, and then inside the not we have another OR, and then inside that OR we have a another OR, okay, and then inside that OR, I mean, you guys get the idea, right? I mean, we have the negation of P, so we have the negation of. So now we have to go back to the spreadsheet, and because we need to look at the columns. So column B is P. Okay, so there we go. All right, so P is column B, and this is going to be B2. And then the other side is just Q, so that's going to be C2. And then the other end of the OR, so this OR here is referring to this OR, and that is an AND operation. So you specify an AND. Oops, okay, commerce. So we have an AND here, and inside the AND there are two things. The first one is Q, which is what, C2, and then the other one is not R, so it's not R. R should be D2, and so on. Okay, I'm not going to finish this entire thing, but you guys get the idea, right? It's just converting what we normally understand as infix notation into a more or less prefix notation, because in the prefix notation we use a prefix to specify what we are going to do, and then we specify the values. So all function calls are basically in prefix notation. So it is tedious, okay, but it's doable. Okay, so once you have an equation like that, you put it back into the spreadsheet. Okay, so you put it back into the spreadsheet. So you just have a long, huge expression here, and then just kind of drag it down. So now you have the true false values for each row for that expression. So as soon as you derive the next one, or if you want to skip like every 3 steps and just want to kind of spot check your derivation, spot check it. Okay, so you just end up with a few columns, and they should have the same values. Okay, so every single row should have the same values for the expressions that are supposed to be equivalent. So if you spot one that is different, that means your derivation has a mistake somewhere, going between those 2 steps, and then you can go back and try to fix it. So yes, so it can be done. Okay, this is one way to do it. The other way to do it is just to use a C program, and using a C program, you can generate this kind of format, kind of the same way. So n is going to be a variable that you're going to use in a for loop. So n is still going from 0 to 31. And then for each value of n, you are going to initialize the values of each element in an array of, in this case, 5 Boolean variables, right? And then you refer to the 5 Boolean variables in the expression, and then you compute, the expression, and then you compute the other expression, the one that's supposed to be equivalent to the first one, and you just have to check that they are the same. So many ways to do the same thing. I'm just pointing out one way to do it that does not involve actual programming. It requires the use of a spreadsheet. Alright, so I'm going back to the text channel. Started with counting in binary and just ended up memorizing it eventually. Worst is when your CNF matches the original truth value except for one. Yeah, okay, so there's okay, so that one that you're missing, that usually will give you an idea, hopefully, of where you might have made a mistake. So so there's that. Alrighty, and someone may be pointing out and go like, but Tech, can we do this in the exam? The answer is, yeah, you can do it in an exam. I mean, you can, during the exam, you can come up with a table like this and populate these columns as you are working on the questions. Okay, I really don't think it's a good idea because this does take a lot of time. So I would say this is a good tool to use when you're practicing. But once you get the hang of actually doing the conversion, then you can kind of not have the training wheels anymore. And then during the exam, it does take a lot of time. And I can almost guarantee you that most people would end up with different expressions. Yeah, so I'm telling people ahead of time so that they don't even bother trying to go like, so this is my expression. What is yours? Different. How about yours? Different. What about yours? Different. Yeah, that's going to happen in the exam. I pretty much make sure that's going to happen. Yep. Yeah, so only if you have enough time. So time dilation is a possibility. Einstein has already theorized that it can happen. I'm not really sure how practically you can make it happen during the exam, but something to ponder upon. Alrighty. But I'm showing you a way, right? This is a way, so that you can actually check all the steps as you derive, the CNF in the homework assignment. And it is a good way to verify your answer, so that you can spot check your own derivation. So if you tend to make a certain type of mistake, or if you have a misunderstanding of a particular derivation, you will be able to spot it. Okay, and that's the whole purpose of the assignment, is really kind of to force you to utilize what you have learned, okay, and practice it. And once again, you can just come up with some random expression here, and and try to turn it into a CNF. Alrighty. Faster than light vehicle. Yeah, that can go back in time. That's beyond just dilating time. It's actually going back in time. All right, Back to the Future, right? Alrighty, so I don't see any other questions regarding the homework assignment. So I'm giving you guys this tool. Okay, I'm saying that use this kind of tool, whether you use a C, C++ program or JavaScript, or use a spreadsheet. That's entirely up to you, but it can be done. Okay, using a truth table is a very visual way to look at two different expressions and see if they mean exactly the same thing. So I would strongly recommend you to at least give it a thought. Okay, if you don't need it, okay, that's fine. But if you want to give it a try, it's there. All right. So with that, put away, we are gonna continue with the counting module. So now we're going to go to the terms for counting, because trial, experiment, and outcomes are all very kind of technical terms when we use those terms in counting and discrete probability. So we'll start with a trial, because a trial is the simplest thing. Okay, it is basically something happening. Okay, and it is a single event. I shouldn't use the word event, but it's a single thing happening. So I'll give you some examples. Right here, it doesn't quite give you an example. So flipping a coin is a trial, okay, because it's something that you do. It's an action, and it has some possible outcomes. Okay, drawing a ball out of in a lotto game, taking a ball out of the basket, that is a trial. When you're transmitting, serially, bits, the transmission and the reception of one bit is also can be considered as a trial, because you can receive the bit correctly or you can receive it incorrectly when you're doing Wi-Fi communication in a noisy environment. So, do we have any questions about what a trial is? It's because a trial is the most simple step of all of these terms. So if you're playing, Dungeon and Dragon games, throwing a dice once is a trial. Okay, so we're good there. All right, excellent. So the next thing is a trial usually has a set of possible outcomes associated with it. So in this class, because we're dealing with discrete stuff, okay, so the possible outcomes are usually finite and it is countable. Well, it's finite, so it's automatically countable. So we are not dealing with some continuous type of outcome, which is a whole different type of analysis. Each outcome represents a possible result of a trial. Okay, so in the case of flipping a coin, it's pretty easy, right? The two possible outcomes would be either head or tail. If you're throwing a six-faced dice, okay, it's 1, 2, 3, 4, 5, 6. if you're drawing a card from a card deck, okay, that can be a little bit more complicated because it depends on whether it's a full deck or whether some cards are already removed. And the same thing applies to drawing a ball out of the lotto in the lotto context, because it also depends on what numbers have already been drawn. But the idea is every trial has a set of possible outcomes associated with it. So an experiment is essentially a series of trials, which means the ordering is important in this case. So an experiment is a series of trials where subsequent trials may be affected by earlier ones. So in the case of flipping a coin, it does not. Okay, there's no effect from one trial to the next. Unless people count, but you might deform the coin just a little bit depending on how it lands. But we are not going to count that. Okay, so if we're not counting the deformation of a coin, then the two outcomes would still be kind of the same, right? Head or tail. If you're talking about throwing a dice, kind of the same thing. A six-faced dice is not going to become a five-faced dice just because you have thrown it once. On the other hand, if you are drawing some marbles out of a bag, okay, and not putting the marble back into the bag, then an earlier trial will affect what outcomes are possible in later trials, okay, because once you have taken something out of the bag, that something is no longer available for further trials. So we'll talk about that and kind of investigate how to model that. So in general, the outcome set of an experiment. So there are two kind of outcomes. One is the outcome associated with a single trial. But when you have an experiment, which is a series of trials, then the experiment itself also has an outcome set. Okay, and each element of that outcome set is representing one way for an entire experiment to finish. All right, so this is a lot of talk, and let's go take a look at some examples. So we'll go ahead and look at one example, which is to flip a coin 3 times. Okay. All right. So if you flip a coin 3 times, each trial has 2 possible outcomes. And if I were to use a set to represent the outcome of each trial, it's going to be either a tail or a head. There we go. And since we also want to have an experiment, because we are saying flip a coin 3 times, so that means the experiment has 3 trials. So in this case, the outcome set of the entire experiment, okay, so the outcome set of the experiment, which is usually represented using uppercase omega. So that's going to be in tuples. It's going to be head, head, head. Okay, head, 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 tail, and so on. Okay. So do we have any questions at this point about these terms? What is a trial, and what is the outcome set of a trial itself? What is an experiment, and what is the outcome set of an experiment? All right, cool. So the outcome set is all possible outcomes and not just for a particular sequence of experiment. That is correct. So each element of the set is representing a possible way for an entire experiment to happen. So each element, which is a tuple in this case, because remember, ordering is by default important. So we basically just have different tuples here, and each one is representing a possible way for an experiment to end up. So in this case, what do you think is the cardinality of omega in this case? I'm just gonna pose that question and have you guys to think about it a little bit. And Marco is correct that HHT head head tail is considered different from tail head head in this sense. Yes. Because it's always possible to combine things that are order dependent back into, kind of merge them back into one thing. We can figure out, that number pretty easily. That is correct. So unless we specify, the ordering is not important. So to analyze a problem, that's one of the things you have to consider is ordering important? Because if ordering is not important, it's a little bit different. The way we look at these things would be a little different. But at this point, we are going to look at things from the perspective that ordering is important. So Dalton is correct. It is 2 to the power 3. The cardinality of this omega is indeed 8. And one other way to look at this, because if each trial has two possible outcomes, you can always just look at those two outcomes as zeros and ones, right? So it basically becomes a binary number. So in this case, because we have 3 trials, we're looking at a 3-digit binary number. And if you remember from assembly language programming or some other classes, the largest unsigned integer that can be represented by 3 bits is 111 in base 2, which is representing 7. So you might say, but 7 is not 8. Well, yes, 7 is not 8, but remember we have to start counting from 0, 0, 0. So when you go from 0, 0, 0 all the way up to 111, there are actually 8 binary numbers. So there we go. All right, excellent. So we have figured out that part. And I'm going to take row now, just so that you can get it out of the way. And let's see. I just worked on this earlier today, and then I have forgotten what word I had chosen for this row taking activity already. So it is trial. There we go. All right, so I'm going to paste it into the text channel and give you guys the 15 minutes that you need to copy and paste trial into the so-called quiz. I wish Canvas in terms of specifying the due date has a way to say 15 minutes from now, right? Nope, doesn't do that. So 15 minutes from now is going to be 12:50, right? All right, there we go. And the other thing that's interesting about Canvas is it doesn't understand 24-hour format either. So there's no such thing as 13:20 if I want to specify 1:20 p.m., which I find kind of annoying because as a programmer, I pretty much prefer 24-hour format. It's actually a whole lot easier to parse. It's a whole lot easier to do computation with. But Canvas doesn't understand 24-hour format. It has a very specific date time format that it understands. And a month must be specified using the name of the month, and you cannot just use numbers. So you cannot say 2022-03-23 to mean today's date. It has to be March has to be spelled out. Okay, it can be abbreviated as MAR, but it has to be spelled out. It's definitely not programmer friendly. Yes, there's that too. Nathan is correct. For computed answers, okay, at least if the actual answer is a 0, if you enter 0 as the answer, Canvas will think that you have not entered an answer at all. So for that, I know I'm digressing, but I'm going to digress a little bit here because some of you will encounter that problem in programming, because it has to do with what can be considered as false, okay, in most scripting languages. So I'm gonna put this one, somewhere, hopefully not too distracting. Okay, so in most scripting languages, you can basically specify an empty string. So I'm gonna use, okay, let me use a JavaScript over here. There we go. All right, so this is a block code in JavaScript. So the expression of an empty string can be considered as false the value of null can be considered as false, undefined can be considered as false, 0 can be considered as false, false itself obviously can be considered as false. So there's a whole bunch of stuff that can be considered as false. So in the case of Canvas, the problem is they probably chose to use a very kind of relaxed way of checking whether something is false or not. So instead of actually checking whether it is an empty string in the text field, they just go like if not, okay, and then the text field. So if that is the context, then JavaScript or PHP or any one of those scripting languages is going to look at all of these things, right? So it basically check all of these things can be considered as false. And that's why when you enter an actual value of 0, it is still considered as false, and it will basically say you have not entered an answer, even though it is an answer of 0. That problem has been reported. I personally reported that problem and suggested this potential bug, why it is doing it, like a few years back, okay, when we first started to use Canvas, and it is still not fixed. So there's that. And this is not libel because I actually have proof that I submitted that bug report back in a few years back. So that is really kind of, it tells you what kind of a company in structure is, when such a simple thing cannot be fixed in a few years. Anywho, we're gonna move on and talk about general counting. So generally speaking, we are counting the outcomes of an experiment. Now, the reason why we want to count the outcomes of an experiment, or why we care about the cardinality of omega, is ultimately because we want to figure out probability. So assuming that the chances of getting each possible ticket from a lotto game is identical, I want to know how much money do I have to spend if I were to purchase lotto tickets randomly and be able to get the jackpot. Okay, so ultimately we want to get to the probability, but to get to the probability we need to know the cardinality of omega. So that's why we are interested in counting the outcomes of an experiment. So in the case of lottery, we may be counting the number of unique lottery tickets. Let T of I represent the outcome set of trial I, where I is 0 oriented, which means the first trial is going to be the outcome set of the first trial is T subscript 0. In the case where T of I does not influence T of J, where J is greater than I, so what is that saying, right? Tech start to use English. Stop using these mathematical symbols. Well, all that means is an earlier trial does not influence the set of possible trials for a later trial. That's basically what this sentence is trying to say. So the outcome set of an experiment of M trials is as follows. So it is T0, Cartesian product with T of 1, Cartesian product with T of 2, Cartesian product with blah blah blah, all the way down to T of M minus 1. So that's kind of like, okay, that seems to make sense, right? So in very simple cases, there are cases where it's a lot simpler than most of the other cases. So Cartesian product is used because for every element of T0 as the first actual outcome from the first trial, every f of T of 1 can be the outcome of the second trial, and so on. So that's why we use Cartesian product, because for each possible outcome of the first trial, it can be paired up with every possible outcome of the second trial, and so on. Now remember, this is assuming an earlier trial does not influence the outcomes of a later trial. So so if you're dealing with lottery, that's not the case, right? Because once you remove a number from an earlier trial, that number can no longer be available to a later trial. So the analysis will be a little bit different. So if it is a strict Cartesian product, then for counting purposes, okay, if we want to know the cardinality of omega, it would become this equation here. The use of pi is kind of the same as similar to the use of sigma. So instead of adding, this is basically just multiplying. Is that notation okay, or does anyone want me to kind of expand it a little bit in a more casual way? Alrighty, nobody. Oh, okay. All right. Okay, so we can do that. All right, so I am going to copy and paste the equation here. So you can do the same thing if you want to understand how something like this is entered. Just go here and copy the clipboard, and then I switch to the second. This go back to this pane here, and let me find out where I need to insert this. I'll put it here. All right, so this thing is essentially the same thing as t of 0. Oh, okay. The cardinality of t subscript 0 times the cardinality of t subscript 1 times blah 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 all the way to t subscript of m minus 1. So it's basically just a bunch of multiplications. And these are all cardinalities. I forgot about the vertical bar here. There we go. So is that okay? Does everybody understand, what the uppercase pi is representing? It's basically, the instead of addition for sigma, this is multiplication, but it really means the same thing. We are just expanding. It's basically a loop. Okay, you can look at this as a loop where I is the index variable. It goes from 0 to m minus 1, and then for each iteration, we are multiplying t subscript whatever I is, or the cardinality of that, to the overall product. All right, cool. And Philip is typing something. I'm gonna wait. So m is the total number of trials. Yes, so m is representing the number of trials. Yep, there you go. All right. Yeah, I think I use m somewhere. There you go. So an experiment of m trials. So m is explained here. So in some cases, the set of outcomes are the same for all trials. So if you're flipping a coin, guess what? Every single t subscript something is going to have two items, right? Because it's either head or tail. So in those cases, it's much easier to deal with this notation, because t of I, no matter what I is going to be some number n. Okay, I'm just going to use the number n here. So that means when you look at this product here, it really just boils down to n to the power of m. So in the case of flipping a coin 3 times, n is 2 because each trial has 2 possible outcomes. M is 3 because we have 3 trials, because each time we flip a coin it is a trial. So 2 to the power of 3 is 8, and 8 is indeed the cardinality of omega in that case. Alright, so are we doing okay so far with section 3? Section 3 basically talks about something that's kind of easy to deal with, and then section 4 has to deal with something that's a little bit more tricky. What do you mean that the outcomes are the same for all trials? So if you're flipping a coin, then every single trial is going to end up with either head or tail. So that is an example of all the outcomes are the same for all trials. If you're throwing a dice, okay, let's say a 6-face dice, the set of all possible outcomes would be the same for every single trial, because you're going to end up with one of the 6 numbers on the surface of the dice. So that's what I meant when I said the set of outcomes are the same for all trials. All right. So we got a few people typing. I'm gonna pause and wait a little bit. What if both sides are head? Then you label one of the heads as tail. Okay, so that seems a little weird, but makes sense. Mm, I mean, there are a lot of examples where, every trial has the same set of outcomes. I mean, it doesn't matter how you label. I mean, if you want to draw a picture of a head on both sides, of a coin, that's fine. But there are still unique outcomes. There are two actual unique outcomes from every experiment, from every trial, I should say. All right. So we got Elijah and Mohammed typing. So I'm gonna wait until they're done typing and then address those points before we move on to a more tricky kind of counting case. I said tricky, but we have already talked about it on Monday, so it really should not be that super tricky. All right, I always see each outcome as different because it can be head or tail. But we are not really looking at the outcomes, we're looking at the set of outcomes. So we are looking at what can come out of a particular trial. And if you flip a coin, then the outcome can only be a head or a tail, or one side or the other, right? So that's why, no matter how many times you flip that coin, it's still going to be one side or the other. And therefore, every single trial, has the same set of outcomes. And then Mohammed said the guy used to win every flip, only got discovered once. He died heroically. Okay. Alrighty. So the next topic is about without replacement. Now, without replacement is just kind of imagine you have a bag, okay, and you put in, slips of paper, okay? So you basically write down a bunch of, each slip of paper has a unique number. We'll just say they're sequential numbers, okay? So 1 to 6, for instance, okay? You got one piece of paper of 1, one piece of paper for 2, one piece of paper for 3, and so on. So you crumble up those pieces of paper, you throw those, little balls of paper into the bag, and now you're asked to, so each trial in this case is to remove one sheet of paper or one little ball of paper from the bag, but don't put it back in, okay? So now we get a little kind of tricky case because, every time you take away something, it does influence the set of outcomes for the later trials because a particular item that is removed can no longer be available for the later trials. Yeah, so if raffle is done correctly, it is the same thing too. I have to say if done correctly because, not sure what m minus 1 is. There's no context for that m minus 1, so I'm not sure what Mohammed is referring to. All right. Alright, so let's assume we start with a set T where n equals to bar T bar. In other words, the first trial, or T0, is going to start with, a certain number of possible outcomes. If E0 of T is the actual outcome of trial 0, then E0 is no longer available for trial 1. Trial 1 therefore has an outcome set of everything in T except for E0. And if somebody is asking, but why do you need braces surrounding the E0? I'm gonna pause and let someone else answer that question. So I'll have one of you guys answer that question. Why do I need braces surrounding E0 if I just want to say, okay, this is a set, it is the same as T, just about everything is there except for E0. T is a set is one thing, but that doesn't answer the question why we need braces to enclose E0 when we are using the subtraction symbol here. Nope, that is not the answer. The answer has well, okay, the answer is not about T, it is about the operator. So Difference or subtraction is an operator that requires one set on the left hand side and one set on the right hand side. And E0 by itself is not going to be a set. Now, if E0 itself is a set, that's fine. But it's still not what we want to specify, because we want to specify E0 used to be an element of T and now we are removing it from T. So that's why in this case the braces are necessary. Otherwise we have a type mismatch error. All right. Yeah, because this set here, in this case, is a singleton set, which means it's a set with only one single element. But it's not, in general, the subtraction operator does not require this set to have one and only one element. It can have any number of elements, including 0. So that's why we have to put braces here to emphasize that this guy here is a set. All right, so there are now, bar t minus the set of E0 bar is n minus 1, because we started off with n, and now we take one element out of t, and there are n minus 1 choices in trial 1. So using E of I to represent the actual outcome of trial I, it is easy to see that for each trial I, the outcome set is going to be it's going to be t minus, and then we have so this is kind of the same thing as a sigma, or a pi, except in this case we are using a union to connect all of the pieces generated by each loop of the for each iteration of the loop. All right, so we still have some more text items from the text channel. Elements are being removed from the set T, so braces emphasize that elements being removed are part of the set. Nope. No. That's not why we have braces. We have braces because subtraction only works between sets. You cannot have T minus E0, because then you have a type mismatch error. E0 has to be a set in order for subtraction to work. Alrighty. So you might want to go back to the discussion of the set operations, I think in week 2 or so, week 1 or week 2, because that's when we talk about, what subtraction, is in the context of set operations. All right, no problem. All right, so in this case, we have the outcome set of the of trial I is going to look like this. So are there any questions about this expression? So we are looking at this expression, we are staring at it, and are there any questions? Can I break it down? Should be good once explained. What do you mean by explained? This is self-explanatory. This is the best kind of coding. It is self-explained. All right, so notations, right? So the first thing we need to understand is, what is this notation here? This is a big U, and J is an index operator. It is an index variable, I should say index variable, and the range of J goes from 0 to I minus 1, and then each item generated by an iteration of the loop is a singleton set that consists only of E of J. Okay, so E of J means E of 0, E of 1, E of 2, all the way down to E of I minus 1. So what exactly are those things? Well, E of I is representing the actual outcome of trial I. So that means we are looking at all the trials prior to trial I, and we say, okay, let's make a gigantic union, which is going to be a set, right, of all of those elements that have been chosen in earlier trials compared to trial I, and then make a gigantic set of that. And that set is representing everything that I cannot use for trial I. So I have to remove that set from T in order to figure out what is left for trial I. So that's basically the explanation of this expression here. And Luke is correct. So it's a shorthand, or it's an abbreviation of T minus, in parentheses, the set of E0 union with the set of E1 union with the set of E2, and all the way down to the E of subscript I minus 1. And we start with 0. Yes, it is 0 oriented because it is stated here, right? E0 is the actual outcome of trial 0. So we count from 0. So that means, starting from 0, we have, by the time we get to trial I, we would have I trials already. And we need to remove, all the things that we chose for those, I trials in order to figure out what is available for trial I. All right, not including E of I because it will be chosen from this difference. That is correct. So Nathan is correct. So basically the symbol represents iterations of elements over the union. That is correct. Yep. So all the moving parts involved here is what E of something is representing. So E of something is basically representing what was chosen by a specific trial. And then the big U notation is basically specifying a loop where the index variable j goes from 0 to I minus 1. For each iteration, we are producing a set, which is the set that only consists of E of j. So the question is, what do we do with the set produced by each iteration? And the answer to that question is we just form a union of all of those sets. Just like in sigma, okay, if this big U is sigma, we are adding the number generated by each iteration. If this is uppercase pi, we are multiplying all the numbers generated by each iteration. So in this case, we are just doing a union of all the sets that are generated by each iteration. So there's your notation. And as a result, the number of choices is n minus I because there are I items. And how do we know this union is not going to have duplicates? In other words, if how do we make sure that there are no two iterations given us the same element, and therefore when you look at the union, it's going to be less than I. So how is that not going to happen? How do we know that is not going to happen? Well, by the very nature of, okay, so the question is, how do we know there is no, okay, what is the term? There's no intersection, right? For each set generated by all of these, by the iterations, how do we know there are no intersection of non-empty sets, from, these sets that are generated? The key is the title of this section. What is the title of this section again? Without replacement, right? So that means we cannot possibly choose the same item twice from the bag because it is without replacement. Once we take something out of the bag, there's no way it can be chosen again. So that's why we can say there are I elements in this big U notation. And that's why we can also say the number of elements left for trial I to choose from is going to be n minus I. All right, because union does not necessarily say that the number of iterations is going to be the same number I here, because what if those sets have intersections, right? If they have a non-empty intersection, that means the actual cardinality of this union can be less than I. But we make sure that's not going to happen because of the very nature of how we choose the E of I's. Alrighty, so moving on. So now for counting purposes, an experiment of M trials is going to have the following possible outcomes. So this is the cardinality of possible outcomes for an experiment that has M trials, where the first trial has n choices to begin with. So M and N are both defined in this case. So are we clear, about what M is representing and what N is representing? All right, so Danny says, is this notation something we see on test? We will see on the test, or will we just be using P of NM? Okay, so I think there are two separate questions there. So one question is about the pi notation and the big U notation. Once it's introduced in this class, it is in the scope of a future exam. So that's one. Now, number two is, is there a different way to express this? The answer is yes. However, we want to know how it is derived, right? So that's why we are going in this, going on this route here, is to say, okay, there are m trials. Trial 0 is the first trial. Trial m minus 1 is the last one. So this I here is really just an index variable to go from the first trial to the last trial. Now, we already have come to the conclusion that trial I has n minus I as its cardinality for the set of trials. So if we want to figure out, how many total outcome do we have for the entire experiment, then we want to multiply n minus I as a term when I goes from 0 to m minus 1. So does everybody understand what this part here is representing? The part that is to the left hand side of the equal symbol. We are trying to figure out the cardinality of the entire experiment, which has m trials, and then the first trial has n choices. Alright, so now we go to do some algebra, and some people may say, but this does not look like algebra at all. Well, trust me, it is algebra. This is actually just algebra. There's nothing fancy here, just notations. Alright, so going from here to here, what am I doing? Can someone point out what kind of seemingly unproductive thing tech is doing in this case? Exactly, so Eric is correct. I just multiply this whole thing by 1. And why? Because even though this expression here seems kind of awkward, starting with m and it goes to n minus 1, blah blah blah. But if you look at the numerator and the denominator, they are the same, right? So that means we are dividing a particular value by itself. And someone's gonna say, but that's just 1. Why would you want to do something like that? Well, that's because this is what enables the magic to happen between the first line and the second line. So to go from the first line to the second line, what just happened here? How can I start with 3 pies and end up with only 2? Yes, I could have eaten one of them, but that's not what happened. So what just happened here? Now you can see the denominator is the same, right? So the denominator here is the same as the denominator here. So that means, that's not the one thing that we did something with. So it has to be the numerator with whatever is outside of the fraction. And somehow I combined this pi notation with this pi notation, ending up with this pi notation here. Matching the boundary values. Okay, so Danny made a very good observation, because where this pi ends at m minus 1, this one starts with m. So that means this pi notation here is really just a continuation of this pi notation here. So that means we can now say, oh, so that means this goes from n minus 0 to n minus m minus 1, the whole thing. And then this one here is going to start with n minus m, and all the way to n minus in parentheses n minus in parentheses n minus 1, which is just 1, right? So it just multiplies all the way down to 1 from n itself, because I starts with a value of 0. So that's how we combine the 2 pies over here into 1 pie. So basically, if you want to imagine actual pies they can buy, they can eat, we are basically making 1 bigger pie out of 2 pies. All right. And then what happens from here to here? Okay, so that's also something that is kind of interesting, because what happened to n minus I, right? How can we just have I left here? So what just happened here? how can I do something like that, right? How can I change the term that is generating the value to be multiplied? It used to be n minus I, but now it is just I. What did I do? So basically, because m minus 1 comes before m, it is just a continuation. Yep, so that explains how we got from here to here. So now the question is, how do we get from here to here? Raising I to from 0 to 1. Nope, that does not account for it, right? All right, so what you need to do is to really spell it out, okay? So you want to get a piece of paper and give yourself a concrete number of n and a concrete number of m. Then you will start to see that, oh, so that means this pi here is a multiplication of because I start from 0, right? So the first term is n. The second one is going to be n minus 1, n minus 2, n minus 3, and so on. And then the very last one is going to be n minus, and then in parentheses, n minus 1, close parentheses. So that means, oh, so n minus, in parentheses, n minus 1, that's silly. That's just 1. And you'll be right. So that means this pi here is really just multiplying all the natural numbers from 1 all the way to n. And guess what this one is doing? Same thing, right? Yeah, this one is doing exactly the same thing. So I is now starting from 1, it ends with n, and we are just multiplying I itself to the entire product. So by changing the form of what is generating the value, and to change the index variable accordingly, I end up with the same kind of value generated to get the overall product, but it looks different. It just looks different, but it's the same values being multiplied together. So the bottom one is kind of the same deal, okay? Because if you look at the start value of n minus I, it's basically n minus m, and when you look at the last one, it's just 1. So might as well just change it to 1 to n minus m, and the generator of the value to be multiplied is I itself instead of n minus I. All right, so Tom is saying, I'm not understanding it verbally. Would it be possible to get a visual clarification? I'm going to leave it up to you guys, okay? But I will give you a little bit of a hint of what to do with this. So if this is too abstract, which it is, okay, a good way to understand what it is actually doing is to substitute n and m with actual values. Now in this case, there is a constraint, okay? The constraint is you cannot have more trials than there are elements available to the first trial. In other words, m has to be less than or equal to n. And you don't want to start with, okay, let's think about n being 16 and m being 13. That's going to kill you, so don't do that. I would start with some smaller values, such as n being 3 and then m being 2. That may be too easy, okay? Because if the case is too easy, it's not going to show you the pattern either. So you want something that will show you the pattern, but without being too cumbersome to actually work on by hand. So I would choose. I'm going to choose n being 5 and then m being 3. So work with that, expand everything out, and then you will start to see how the derivation works from one line to the next. Is that okay? So I'm going to give you guys this as your own assignment. So I'm turning questions into your own ungraded assignment. So I'll put this into the text channel. So n starts with a 5, m is going to be a 3, and just kind of just generate all of these terms accordingly. Just write it out, okay? What this is going to be, 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 and up to here, obviously, because once we get to this point, we can see that So the top pi here is really just n factorial, because n factorial is defined as, one way to see it is 1 times 2 times 3 all the way up to n. And then the bottom one is kind of the same deal. It is just 1 times 2 times 2 times 3, and we end with n minus m. So the entire thing, okay, starting from here, ending here, is really n factorial divided by n minus m factorial, which we also have this notation of p superscript n and subscript m. That's just a notation. Okay, instead of writing this all over and over again, this is just a whole lot easier to write. That's why. All right, so I'm going to pause here and see if you guys have any questions. All right, no problem. And for those of you who are thinking, but Tech, do you like to use spreadsheets to do everything? So how do we use a spreadsheet to specify this term here, P, N, M? In other words, we have N choices for the first trial, and then we have M trials. How do we specify this in a spreadsheet? No one is actually asking that, okay? But I'm going to answer that question as if somebody is actually asking it. So the answer is per mut. Yes, per mut, not permutation. It's just per mut. So, let me start with sheet 2. So it is just P equals P per MUT. So that's the name of permutations. The first so-called count is the number of things to choose from, which in our case is n. So we'll put a 5 here. The second count is the number of items that we want to choose out of the first one, which in this case is 3, which is the number of trials. So this is how we specify the same thing. Okay, 5 factorial divided by 3, 5 minus 3 factorial, which is 2 factorial, and there are 60 of them. I really don't know the name or the term for that uppercase pi. It's basically, instead of having a sigma to specify the summation of a bunch of terms, basically over a loop, this is multiplying all of those terms. Yeah, it's uppercase pi. Yep. Yep, it is uppercase pi, because if you use LaTeX and just enter uppercase pi, that's what you get. So that's just uppercase pi. Alrighty. Aha. Okay. Very nice. Alrighty. So there we have it. So now we have just looked into counting the number of permutations. Now remember, permutations means ordering is important. Okay, so let's just look at the text channel. We have a bag with 3 balls. Okay, RGB. Okay, so if you're just randomly getting something out of the bag, so you can if I say, okay, here's a bag of 3 colored marbles, and I want you to get 2 out of the 3 out. Okay, so you can get a green one first and then a red one, or you can get a red one first and then a green one. Those 2 are counted as unique cases now, because we are dealing with tuples, and with tuples, ordering is important. So to answer that question of if I start with 3 marbles in a bag and I need to take 2 out of them, how many ways can I do that? Well, it's the permutation of 3 choose 2. In other words, it's per mut 3 2 in that case, which then translates to 3 factorial divided by, in parentheses, 3 minus 2 close parenthesis factorial. Now 3 minus 2 is 1. 1 factorial is just 1. So it basically is 3 factorial, which is 6. Okay, so there's 6 ways to choose 2 things out of a bag of 3 where ordering is important. Does that make sense? Does anyone want to see the 6 ways to do it? I mean, yeah, most of you can probably just kind of figure that out, but it's, I can give you those 6 items, okay? So we can have, red and blue, blue and red, and then we can have red and green, green and red, and then we can have blue and green, and then we have green and blue. So now we have a, oops, okay, so I forgot to mark this as a equation. There we go. So this is matching the picture in the text channel right now. All right, so I'm gonna do you guys a favor, because if I wait, I can do something better. I was about to take a screenshot of this and then paste it into the text channel, but I can do better, right? There's always a better. And right click. Oh, it doesn't do it. Darn. Okay, but that's also okay because this is all from my text, text editor. So I can just copy and paste the text here. Control Shift C to copy, and then Control V here to paste. There we go. All right, where's the rendering? There we go. All right, excellent. Yes, I know someone is going to say, but Tech, can you turn those R, G, and B into actual marbles of those colors? Because I cannot read the letters and associate those letters with the picture. And the answer is, I'm not quite that good with scripting. So somebody else can write a script to convert the R, G, and B into the actual colors and then post it. That is funny, Luke. I am symbol blind. I'm gonna say something that might come back and bite me later, but I'm gonna say anyway. Symbol blind people may not be the best people to study computer science or become, developers and computer engineers or software engineers. I'll just say that because I think by saying this I'm trying to do people a favor. Couldn't drive either. You don't have to, since we have Teslas now, right? You just get in and you just have to tell the car where you want to go. And when AI is sufficiently advanced, you don't even have to specify exactly where you want to go. You can just say the same place that I went last week, on the same day, at the same time, and then the AI will figure out what that is. Yep. All right, so we are running out of time. Okay, it doesn't mean we are just ending the lecture like that, because what I want to do is to show you guys what is after this, and I want to kind of emphasize that it is really important to read ahead, because in this case, these concepts are not super duper abstract, okay, but it does take some time to kind of let it sink in. So I would definitely try to read ahead of time. Let's see, move on. And these notations is a killer. So if you get to this part here and you have no idea what this means, because we have a recursive function, omega is actually a recursive function because we can have omega 2 of something and then omega 1 of something, and generalized to omega I to omega I minus 1. So if you get to this part here and go like, oh man, this is a little tough, you can stop there. Okay. Now, however, okay. For those of you who really want to be able to kind of sink into this, you'll sink your teeth or your mental teeth, okay, your intellectual teeth into this. What you want to do is to give yourself an example, okay? So you want to say, let's start with a set, okay? T has 1, 2, 3, 4 as its elements, okay? And then you say, I want to find out what is omega 2 given that T is a set of 1, 2, 3, 4 using these definitions, okay? Because that will give you a concrete case to work with. So even though, for each level of the recursion, it's a little bit tedious, right? But it will show you, the tree of recursive calls. And then once you look at the tree of recursive calls, the whole thing should go like, oh, so that is what it means. Okay, it's just a matter of understanding the notation and figuring out, how what each thing is trying to say. So there we go. That is cute. Okay, I'm just looking at the text channel. That's kind of funny. I don't know when the next exam is gonna be because I want to make sure that you guys get the whole thing about CNF and resolution. So the resolution homework is going to be assigned next Monday. So I would say the Wednesday after next Monday would be a good day to have exam 2. And that will give me some time to grade exam 1 too, so that people cannot say, we are having exam 2 and where's the grade of exam 1? Yes, I'm still working on it. Yes. Just trying to come up with a good rubric to grade it is, it takes some time. All right. The notation is section 7. Oh, the big U notation. Yep. It's the same thing. It's a recursive thing. You can see how U of I depends on U of I minus 1. So in this case, we are, because U of blah 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 is returning a set of sets, and that's why S here is a variable to iterate through all the elements of U of I minus 1, and each element of U of I minus 1 is a set itself, and which allows us to do the union thing, with the generator expression. So I hope that helps with Luke trying to understand that notation. All right, so I'm going to stop here because you guys need to go do something, other than this class. But don't forget the CNF assignment is due Monday, and I just showed you a way to kind of verify, your steps, which does not mean that you don't have to show the steps. You still have to show the individual steps. It's just that there's a way for you to double check to make sure that all your steps are done correctly. Alrighty, so I'm gonna get off here. So you guys have a nice weekend. I know there's a homework assignment, but nonetheless, you have a nice weekend. I'll see you guys on Monday. Alrighty, bye.